Okay, so we said if we took a bunch of different samples that we were going to get a bunch of different statistics. So when we take a bunch of different samples and look at the sample mean, sample proportion, we're going to get different statistics, and that's called sampling variability or sampling variety. That just means within different samples, I'm going to get different means and different proportions. All right, so in this case, we're going to think back to that table where we had 100 seniors and we took a look at 100 GPAs. So we're going to let p hat represent the proportion of seniors in the sample of 100 whose GPA is 2.0 or higher. So I have one sample, 100 seniors. P hat is the proportion whose GPA is 2.0 or higher. All right, so notice how this says P hat 1, P hat 2, P hat 3, P hat 4. This means I took one sample of 100 seniors, 78% had a higher than GPA of 2.0. Sample 2, the proportion of students that had a higher then 2.0 GPA was 72%. So in proportion 3, 81% of the 100 students had a GPA of 2.0 or higher. So notice how I have 10 samples here, and I have 10 different proportions of seniors that had a GPA of 2.0 or higher. Why? Why are these proportions all different? Well, they're all different because I have a different group of 100 seniors each time. Okay, so all of the P hats are the proportion of seniors in a sample of 100 whose GPA was 2.0 or higher. It's like a tongue twister to say. So if I compare many different samples, the statistic P hat is similar, and when it's similar, that means the sampling variability is low. So sampling variability means if I take a lot of samples, how do the proportions look? Are they widely different, or are they all about the same? So these are all kind of in the, we have one that's 68, but the rest are sort of in the mid 70s to low 80s. I don't have anything that's like a 50% and then an 80%. So the sampling variability is low here because I don't have a wide range of p hat values. Okay, so if I compare many different samples and the statistic is very different, then the sampling variability is high. So if I had like 65, 92, 73, 25, okay, so if all 25%, if all of these were very different, then that sampling variability would be high. So sampling variability just talks about if I'm doing sort of the same sample proportion, sample mean with many different samples, am I going to get similar results, or am I going to get results that are sort of different? Now, what do we do with all of these proportions? Okay, so these are called sampling. Okay, this is sampling variety, but these are samples, and we're going to create a sampling distribution out of all of these sample proportions, and that is called a sampling model. So a sampling model of a statistic is a model of the values of the statistic from all possible samples of the same size from the same population. Okay, so that might sound confusing. The sampling model is putting all the p hats in a distribution or a curve. Okay, so that sounds confusing. All a sampling model is, if I took every possible group of 100 seniors from Fairfax County, okay, and then from those every single possible group of 100 students, found the proportion of students who had a GPA of 2.0 or higher, and then took each of those sample proportions and kind of made like a dot plot out of them, and that dot plot would basically give us a distribution or a curve of what it would look like of all of the seniors in Fairfax County, okay? All right, so if we took every one of the possible samples of size n from population, every single possible sample of 100 students from all the seniors of Fairfax County, calculated the sample proportion for each, so every single time we took a sample of 100, we found the sample proportion and graphed all of those values, every single one of them, we'd get a sampling distribution. So a sampling distribution of a statistic, okay, is the distribution of values taken by the statistic in all possible samples. Okay, that sounds confusing. It's a sampling distribution is literally just taking all of those sample proportions and putting them on a curve, okay? Don't confuse this with the distribution of a sample. A distribution of a sample is just taking 100 students and maybe finding each of their GPAs. So if I took 100 students and found each of their GPAs and put that in a graph, that would be the distribution of a sample. That's a sample of 100 students, their GPAs are on a graph. A sampling distribution takes those group of 100 students, finds a sample proportion for every single one of them, every single group of possible 100, and so I have many different statistics on a curve, okay? Now, it's very, very difficult to take all possible samples of size n to get the whole sampling distribution. So instead, we often use simulation to imitate the process of taking many, many, many samples. So one of the uses of probability theory and statistics is to obtain sampling distributions without simulation. Okay, and oftentimes we'll get a sampling distribution that won't be every single solitary possible sample, but it would be a good representation of the population. Okay, suppose that the sampling model consists of the samples from our 100 seniors and their GPAs, okay? Now, keep in mind there's actually more than 10 possible samples, so we did 10 of them, okay? We took 10 samples of 100 students and found their sample proportion. Now, there's many, many more than that. This sampling model, so that's basically saying if I took all of those GPAs from the 10 samples and put them in a curve, has a mean of 0.754 and a standard deviation of 0.049. So basically what that means is I took all of those p-hats, okay, 10 of them, I put them in a distribution, and then I found the average of all the p-hats, so basically like adding the 10 p-hats together, dividing it by 10, okay, and then I found the standard deviation of all of those p-hats. Okay, now this is a statistic. 0.754 is a statistic because I took all 10 of those samples, found the average GPA for all 10 of those samples, and I used it to estimate the population. If the statistic used to estimate a population or a parameter is unbiased, okay, unbiased, what does that mean? If the mean of its sampling distribution is equal to the true value of the parameter being estimated. So let's say I took all 10 samples of 100 students, so I'd have 10 p-hats in there. I took the average of the 10 p-hats and the standard deviation of the 10 p-hats, okay? If it's an unbiased estimator, then that means that this mean is about the same or the same as the true value of the proportion of students, of all the students in Fairfax County that have a GPA higher than 2.0. Okay, so unbiased means the mean of the sampling distribution is the same as the value of the population. Okay, so let's take a look at what that means. All right, so a little bit tricky. Since the mean of our sampling model is 0.754, then p-hat is an unbiased estimator of the population proportion of students that have a GPA higher than 2.0 if the true value of p equals 0.754. A statistic can be unbiased and still have high variability. So it can be unbiased and still have a large difference between all the statistics. So if you want to create lower variability, you want to increase the sample size. So larger sample sizes are going to give a smaller spread. So think about it. If I take 100 students and find their proportion of students that have a higher GPA than 2.0, that is going to have more variability than if I took 1,000 students and found the proportion of students that have a higher than 2.0 GPA, because I'm taking a look at a larger sample, so it's going to have less variability within that sample. But just keep in mind, no matter what we do, we're never going to completely eliminate bias. We can help get rid of it, but we're never going to eliminate it. Okay, so there are actually 3 distinct distributions involved when we sample repeatedly and measure a variable of interest. Okay, now the next slide is going to take a look at the 3 distributions when we sample repeatedly. So that's when I say when we sample repeatedly, that's just talking about I did 10 different p-hats, okay, that's repeated sampling. The population distribution gives the values of the variable for all the individuals in the population, okay, and we'll talk about this on the next slide. The distribution of the sample shows the values of the variable for individuals in a sample. So I took a sample and put that in a distribution. Population distribution, did the entire population, put that in a distribution. The sampling distribution shows the statistic values from all possible samples of the same size from the population. So the sampling distribution is sort of like taking a whole bunch, it is like taking all the possible statistics and putting that in a distribution. Now I'm going to explain what that means a little bit more on the next slide. And we're going to do that by the process of choosing many random samples of 20 chips, finding the sample proportion of red chips from each one. We're going to take a look at what is the difference between these 3 distributions. Okay, so let's look and see what the difference is between a sampling distribution versus a population distribution versus the distribution of a sample. All right, so let's just say that we have a giant bag of blue and red chips, okay? So we have 100 blue chips and 100 red chips. So if we were to make a population distribution of those chips, based on the proportion, what's the proportion of blue versus the proportion of red, the frequency or the proportion of blue would be 100, the proportion or frequency of red would be 100, which would make them each be 0.5. So there's 100 of each, so the population proportion, which is the parameter, is 0.5. Okay, so that's looking at every single solitary chip. All right, now, distributions of a sample data. So this is, let's say we took a sample of 20 chips, and then on my graph from that one sample and that one sample only, I said, what is the frequency of blue versus what is the frequency of red? Then that p hat that I calculate is the proportion of red chips, but that is just for that one sample of 20, and that p hat is 8/20. Okay, so then the second one, I do it again. I take another simple random sample of 20. This is just my sample data from that one sample. I have 9 blues and 11 reds, so my sample proportion of reds just from that one sample is 11/20. Do that again. This is just the sample. This was my population distribution, everything. This was 3 individual samples, so that's the distribution of the sample. Then the sampling distribution, what it does is it takes each of these individual p hats and puts them on the graph. So this p hat of 0.4 would go right here. This p hat of 0.55 would go right here. This p hat of red chips 0.65 would go over here. And I would take hundreds and hundreds, every single solitary possible combination of 20 chips, and I would plot the proportion of red. So each one of these dots is representing p hats from one individual sample. Now if we look at this, okay, we can sort of see the mean of this sampling distribution, because this is a whole bunch of p hats, is about 0.5. So this means that it's an unbiased estimator because it's close to the population proportion of red, which is 0.5. Okay, the first one was all of the data. The second one was the distribution of each sample of data. And the last one was a distribution of all of the samples. Sampling distribution, distributions of sample data, and population distribution. Just make sure you know the difference between all 3 of the names. Okay, all right, so a statistic which is used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter being estimated. So in this case, that's saying what is the average of all of these proportions. These are a whole bunch of p hats. What is the average p hat? So if we did 100 samples, we'd take 100 p hats, add them together, divide by 100, and get what that average is. That's 0.5. So the average is 0.5. That means that the mean of this sampling distribution is unbiased if this mean of all the proportions is the same as the population proportion, which is 0.5. And in this case, it is. Okay, so the center, there can be biased and unbiased estimators. Our goal is to get an unbiased estimator when we do the samples. So in the chips example, we collected many samples of size 20, calculated the sample proportion of red chips. Okay. How well does the sample proportion, so this is your sampling distribution, estimate the true proportion of red chips, which is 0.5? Now, if we look at this, it's pretty obvious that the mean of all of the sample proportions was about 0.5. We can therefore say the sample proportion estimate is an unbiased estimator for the population because it's the same as what we know the population to be. Okay, so because of the fact that statistics from random samples, they have definite sampling distributions. All right, since they have definite sampling distributions, we can ask the question, how trustworthy is the statistic as an estimator of the parameter? Can we really trust the sample? Is it really the same as the population? To get a complete answer, we're going to look at the center, the spread, and the shape. Okay, notice that the center of the approximate sampling distribution is close to 0.5. Okay, in fact, if we took all the possible samples of 20, we found that the mean of the sample proportions was exactly 0.5.